the last lecture, we began the discussion for Chinese remaindering theorem in context of the polynomials, and we gave the basic background. We had established a few results. First one was the division property that polynomials have, that is, for all polynomials f and g, there exists unique q and r such that f can be written as q times g plus r, where the degree of r is strictly less than the degree of g. This is a property very similar to the integers. The second property that we had was the existence of a GCD. We said that for all P1 and P2, there exists a GCD of P1 and P2. This is a polynomial which divides both of them, and anything else that divides these two also divides this. We also noticed that if the GCD of two polynomials is 1, that is to say, if the P1 and P2 are co-prime, then if P1 divides another polynomial u, P2 divides the same polynomial, then P1 and P2, their product divides u. And this we can extend to n polynomials. If you have a set of n polynomials which are pairwise co-prime and each of them divides u, then the product of all the n polynomials will divide u. We had also written some properties of modulo computation. Now we are in a position to state the Chinese remaindering theorem, and the statement as well as the proofs are almost identical. There is no difference. Only difference is in case of integers, we were looking at the value. Here we will be looking at the degree of the polynomials. And the theorem says that if we have n polynomials are pairwise co-prime, and P is the product of all these polynomials 0 to n minus 1, I should say, then there exists a 1-to-1 correspondence between, on one hand we have the polynomials u, so I would simply say, of course they are all, these are all members of polynomial over one variable. So all those polynomials which have degree strictly less than degree of u is strictly less than the degree of p. So on one hand we have this set of polynomials, and in addition to this we have this tuple of polynomials, n tuple, of polynomials, we call them u0, u1, un minus 1, where the degree of ui is less than, strictly less than, degree of pi. Okay. The 0 is also included in this set, and similarly 0 is included here as well. This one-to-one correspondence we can show in the following way. Sorry, I have to put a condition that this correspondence is such that the image, so u actually goes to the tuple where the first element is u modulo p naught, the second is u modulo p1. So this correspondence is unique, and the proof, it is easy to establish that for every u we have such a tuple, because all we have to do is compute the remainder of u with respect to p0 and p1 and p2 and so on. So the forward image is trivial. It is the thing that we have to show that this map from u to this is one-to-one, and then we will show it is onto. Now, to show that it is one-to-one, we will use one of the results that we have discussed. Suppose u and u prime both map to the same tuple. Let us state that as R0, R1, Rn minus 1. If both map to the same thing, which simply means that u modulo p0 is R0, similarly u prime modulo p0 is R0, and so on. Then u minus u prime modulo any pi will be Ri minus Ri would be 0. This is for all I, and that implies that pi divides u minus u prime for all I. So every one of these pi's is able to divide this polynomial, but our assumption is that all the pi's are pairwise coprime, and we have earlier argued that in that case, since pi's are pairwise coprime, the product of pi's, product of pi's, which is same as p, divides u minus u prime. Now, u and u prime belong to the first set, and this set contains all the polynomials of degree strictly less than the degree of p. So, you have a polynomial p here, and a polynomial of degree is strictly less than that of p, and then if p divides it, simply means u minus u prime has to be 0, since degree of p is greater than the degree of u minus u prime. That means u is equal to u prime, and that establishes the one-to-one nature of this map. And so this was exactly the same argument we had offered for integers. Similarly, to show that this is onto, what we have to do is to show that the map is onto, we are going to pick an arbitrary element from this set and give a polynomial u such that the image of that u is the one that we have picked. So let us take pick arbitrary polynomial, n tuple of polynomials u0, u1 through un minus 1, where each has degree less than the degree of the corresponding p. So ui has degree less than degree of pi. We claim that this sum ci di ui mod p, the image of this polynomial is this. Now let me just explain what is this. Recall, as in the case of integers, ci is nothing but p by pi. So let us just write down, where ci is p divided by pi, di, which has degree strictly less than the degree of pi, is a polynomial such that ci times di modulo pi is 1 for every I. In other words, di is the multiplicative inverse of ci. If such a di exists, then this sum modulo p is a polynomial whose image is again this. Now, so there are 2 points again we have to argue that di's exist, and 2, the image of this is indeed this. But image of this is this simply means that when I compute modulo pi of this polynomial, I should get ui, then we are done. So let us first take that. The sum I ci di ui mod p and the modulo pi of this From our last lecture's exercise, we noticed that this is a product of pi and some other p's. So this thing is same as sum ci di ui mod pi because pi is a factor in p. and Pi is also a factor in every Cj other than Ci. Remember, Ci is there. So, in Ci we do not have Pi, but every other Cj has Pi up there, and that makes this modulo computation easy, because that would be 0 for those terms, and this will reduce to simply Ci, Di, Ui. All right, I would probably apologize for the indices. Let me make them j here, just to not to confuse these indices with this. This is bounded here, so I'll just make them j. All the j's other than I vanish, and you are left with just this term in the sum, and then of course you still have modulo Pi, but this we again yesterday we saw Ci Di, I can always say this as mod Pi into Ui, then again mod Pi, and this is 1. So, this simply reduces to Ui. The reason is the polynomial Ui has degree less than that of Pi. So, it does not really affect Ui, and this is what we wanted to show, that the image of this indeed is what we had started with. The existence of these DIs comes from the fact that Ci and Pi are co-prime. They do not share any factor, any non-trivial polynomial as factor, because Pi has no polynomial factor with any Pj, and hence it does not have any factor with the entire product of Pj's without Pi, and therefore, the GCD of Ci and Pi is 1. And once again we had seen yesterday that in this case as well there exists some polynomials alpha and beta. So, there exists alpha and beta in this such that alpha Ci plus beta Pi, beta Pi should be 1. I should be able to express the GCD of the two as this linear combination, and then if I take modulo Pi of both sides, I am going to get alpha Ci mod Pi equal to 1, because this vanishes, and this is all we wanted to show. This alpha would serve as Di. Notice that you can have many alphas, but if you replace this by the modulo Pi of alpha, that is, say you can reduce and divide this alpha by Pi and take the remainder, that will also serve this purpose, and we will actually pick that because it has minimum degree, and that establishes the one-to-one correspondence between these tuples and all those polynomials which had degree less than the degree of P. Now, we will look at the the algorithms for computing the tuple, this tuple for a given polynomial, conversely compute the polynomial from given tuple, and then we will look at a special case today of a special choice of PIs gives an interesting result. Okay. So, once again the algorithms also are identical, and it will be sheer repetition, but let us run through this. Recall that we defined q ji to be the product of 2 to the power these polynomials p I plus 2 power j minus 1, and we defined these terms for I equal to 0 and 2 power j and 2 times 2 power j and so on. Hence, p was nothing but q t0, I think we had used k, let us say k0, where n was 2 power k. So, first we have to compute all these qis, qjis, and for that we start with q 0i are pi's. Okay. So, I would probably have to write down for 0 to n minus 1 do q 0i is pi, and then we will start computing q's of higher level, that is the higher j values. So, for j equal to 1 to k, and for I equal to 0 to n minus 2 power j in steps of 2 power j. Q j I is q j minus 1 I times q j minus 1 I plus 2 power j minus 1. That computes all the ji's. Next, let us compute the n tuple corresponding to a polynomial u, where the degree of u. So, I am computing u to compute the tuple for n, where this has degree, where degree of u is less than the degree of p. So, we will start with u k 0 to be u. Once again we go in through the levels, and we put this into again a j loop and an I loop. So, j equal to k to 1 do, and for I again 0 to n minus 2 power j in steps of 2 power j do. This is do, and u j minus 1 I and u j minus I plus 2 power j minus 1. These are the two terms we have to compute. So, this is nothing but u j I and modulo with q j minus 1 I and u j minus 1 I plus 2 power j minus 1. This is u j I mod q j minus 1 I plus 2 power j minus 1. And when we terminate this loop, we have u0 I. So we return, then we return the tuple u0 0 u0 1 u0 n minus 1. These are exactly the u0 and u1 and so on. And let me also write down the computation of u from the n tuple, and then we will look at the time complexity of each of these. This time, okay, once again let me say computation of u from the tuple u0 through un minus 1. And here we are going to initialize. This is the reverse process that we have to do. And recall that the way we compute this is by first computing di's, but I am assuming here that di's are given to you, and then we are going to compute the u. So let us just recollect that we had s ji's. The definition of s ji was that s 0I was nothing but di ui, and then there was recursion. S j I was S j minus 1 I q j minus 1 I plus 2 power j minus 1, and S j minus 1 I plus 2 power j minus 1, this is times this, and then this is times q j minus 1 I. So this product term plus this product term, this is what we have to compute in recurrence relation. So we will start with initializing s's for I equal to 0 to n minus 1. S 0I is di ui. Okay, so we have this, and then for j equal to 1 to k, and for I from 0 to n minus 2 power j in steps of 2 power j do. And we are just going to write down that relation. S j I is S j minus 1 I into q j minus 1 I plus 2 power j minus 1 plus S j minus 1 I plus 2 power j minus 1 into q, and return S k 0 mod p. The final polynomial that we get, the sk0 is simply the sk0 computed here is nothing but ci pi di summed over here, but we also need to compute mod p of that. Hence, in the last step we are computing the modulo p of this. Now, let us go through the algorithms for the time complexity. The degree of these polynomials will depend on the degrees of pi's. So, let us suppose the degree of every pi is less than or equal to b for all I, whatever be the b. Then this has degree 2b, because both of them have degree less than the degree of pi. Degree of these terms will be 2 to the power j minus 1b, 2 power j minus 1b. There are 2 power j minus 1 terms multiplied here. The terms are pi's. Each has degree at most b, and there are so many of them. So, this term, these are all of degree for j minus 1. These recursively one can establish have degree 2 power j times b. The degree of this is 2 power j times b, bound, upper bound for these. When I multiply this with this, I will have a polynomial of degree at most 2 power j plus 1 times b. So, that is the argument. One of these computations involves, this computation involves one multiplication of size 2 power j times b. M, I would probably clean up this, and let us denote by mx the time to multiply two polynomials of degree x each. So, this step takes m 2 power 2 times 2 power j b. One of these steps takes this much, and then there are n by 2 power j such steps in it, and this we know is less than or equal to 2 m n b. Once again, because this is at least linear. This is independent of j, and we have k such steps. K is nothing but log of n. So, the total cost is the time complexity is order m n b into log n. This is what it takes to compute, assuming of course that di's are given to us a priori. And it is very easy to verify that the complexity of this algorithm as well as the complexity of this algorithm is also the same, exactly the same, is order m n b log n. All of them cost us the same amount. In a lecture later on, we will show that m x is less than or equal to x log x, and later on we will show this, and that indeed shows that the brute force method of computing these is more expensive than this algorithm. So, now I am ready to discuss a special case. In the special case, I am going to take a very specific set of PIs and shows the consequence of these computations. So, now we are coming to a special case of PIs. Let A0, A1, A n minus 1 be some real numbers which are distinct. Now, define Pi as x minus ai for all I. Okay. Then, 1 times Pi minus 1 times Pj is a j minus ai, which is not 0 because these are distinct. So, 1 over aj minus ai times Pi minus 1 over aj minus ai times Pj is 1 implies GCD of Pi and Pj is 1 for all I not equal to j. This is the condition we want to satisfy, and indeed these Pi's are pairwise coprime. Now, let us take this and find out what okay, first of all notice that the degree of P is exactly n, because we have degree 1 polynomials. When you multiply n of them, you get a polynomial of degree n. Now, let degree of a polynomial u be less than n. Then the Chinese remainder theorem says that the image of u under this correspondence is u mod P0, u mod P1. So, what are these? This is remainder of u when divided by x minus a0. So, u divided by, so we are going to get u equal to sum g times x minus a0 plus r. This is from division theorem. Now, you evaluate both sides at a0. So, we get this polynomial u evaluated at a0, we are going to get this at a0. Now, notice that the degree of r has to be strictly less than the degree of this polynomial, where degree of r is less than degree of P0, which is 1. The degree of P0 is 1, hence this is 0, which means r is a constant. So, evaluating at r0, a0 does not give anything else, it is same as r. So, all we notice is that the remainder, or let me call it r0, r0, the remainder is nothing but the value of u at a0. Hence, this is same as u evaluated at a0, u evaluated at a1. So, what we will get for this special choice of PIs is the forward computation will give me the value of u at n distinct points. The points are of your choice, you can choose your points. So, this is, I may call it evaluation problem. So, what we see is that this problem of computing the value of a n degree polynomial at n distinct points, we can do this in order. Notice our b is 1 because all our polynomials have degree 1. So, this takes mn into log n time, and as I told you earlier that we will show that we can multiply two polynomials in n log n time. So, the entire time will be n log square n, which is an efficient algorithm, because a brute force method of computing the value of a polynomial at each point will take order n time, and hence computing at n points will take order n square. So, this is more efficient. The second problem is interpolation. The reverse one. What does it say? It says that given values, let us say V0, V1, Vn minus 1 at points x equal to a0, x equal to a1, x equal to an minus 1, compute a polynomial of degree less than n such that a polynomial, let us call it u, such that u at ai is vi for all I. This is exactly the reverse problem. Now, we are given u at a0, u at a1, which is same as u modulo p0 and so on. This would be u modulo p1 and so on. Given this, we will give you a polynomial u of degree less than the degree of p, which is n. So, this has degree at most n minus 1. We know that if I have two points a1 and I know the values of a polynomial at 2 points, then I can give a polynomial of degree 1, namely a straight line, which will pass through these two. So, this is the interpolation. This in more general sense we can actually compute in this fashion, again in order mn log n. But there is one catch. Now, we have to figure out what are our di's, because that is one unknown entity we did not discuss for the general case. Now, we have a specific PIs. So, I want to know what are di's and how do I compute them, and once we know that, then we should be able to compute the polynomial from its values at n points. This is supposed to be multiplicative inverse of Ci. Furthermore, we will assume that the degree of this is less than the degree of Pi, because we can always do that. Our goal is that Ci di mod Pi should be 1. So, I can always replace this by di mod Pi, take this polynomial, do this and do Pi. So, I will try to compute a constant. Notice di modulo Pi is of degree 0, and I am supposed to find a constant such that that time Ci is 1. Such a modulo Pi is 1. But this is same as Ci at Ai, because when we compute modulo Pi, we are computing at point Pi. That is, the modulo is nothing but computing at that value Ai. This times this entity is 1. So, this entity is nothing but 1 over Ci at Ai. All we need to do is compute Ci at Ai. Now, that is very easy. Now, let us say, suppose f is nothing but dp by dx, dp x by dx. Notice that P is the product of Pi's. This is same as d by dx of P0 times P1. So, if I differentiate by parts, when I differentiate with respect to P0, I get 1, because this is nothing but x minus A0. And what is left? This part, which is nothing but C1. Hence, this is nothing but C0. Okay. When the multiplication of these terms is C0 plus C1 plus C2 Cn minus 1. Now, when you evaluate f at A0, so f at A0 is nothing but C0 at A0. C1 has P0 in it, and at A0 it vanishes. Hence, all these terms will vanish. Similarly, f of A1 is nothing but C1 at A1. So, to compute C0 at A0, C1 at A1 and so on, all I need to do is evaluate f at all these n points and then take their inverses, reciprocals, and then I am going to get my di's. So, all we have to do is compute f, determine its value at all these points. I have di's, and then I am going to go ahead and compute all ui's. So, now I am combining all the steps to compute the interpolation. The first step is I initialize q0i to pi's. In the next step, I am computing all the qji's. These are the same old steps. Here, in order to compute the di's, as I had discussed earlier, we first compute the derivative of p with respect to x, which we know is nothing but C0 plus C1 plus C2, and we have to compute this polynomial at A0, at A1, at A2, and those will give us the di's, their inverses. So, now I am computing the evaluation problem. This is where I start at j equal to k, end up at 1, I is in those steps. Fj minus 1i is Fji modulo Qj minus 1i, and Fj minus I, j minus 1 comma I plus 2 power j minus 1 is Fji modulo Qj minus 1 I plus 2j minus 1. But this is nothing but computing the Fk0 at points A0, A1, A2, A3, and those will be nothing but F0i's. So, we have F, note that F0i is nothing but Fki at Fk0 at Ai. Now, I have f0i, which recall is nothing but 1 over di. Okay. Di is nothing but 1 over f0i. This is a constant and this is a constant, hence this is nothing but ui di. Once we have ui di, this is the same old step, and it leads to at the end sk0, and we compute modulo p. So, the final polynomial that we get is of degree less than n, and its value at ai's is given to be where is my ai? Is this ui. These are our values at various ai's, and this polynomial will evaluate to these ui's. Okay, this is where we complete the discussion of Chinese remaindering.